to do. But let's just review quick, and then we'll finish today's. So we're wrapping up NMR, nuclear magnetic resonance, and you take a gyroscope and you that inner red wheel here is spinning nice and fast, and the whole axis starts, going in this weird line depending on, I guess, the direction you spin the inner wheel here. What is that called? This oddball motion. So there wasn't just the motion. There wasn't just the motion of the inner gyroscope moving. Not only this motion, but you also had this axis rotating around. What was that called? Precession. Right. And that precession occurs at so many revolutions per second, so such a frequency, and we had a name for it. What do we call that frequency? It starts with an L. Larmor frequency, right? So that frequency of precession was our Larmor frequency. Okay. And what region of electromagnetic spectrum are we really using here? Radio waves. Yeah, to interact between what type of matter? Light and matter. But what type of matter in this type of spectroscopy? Proton. I guess we should say proton nuclear magnetic resonance, because there's a lot of different nuclei, right? So we haven't been talking about carbon-13 or phosphorus-15 or whatever. We're just talking about proton NMR, really. Whoa, I'm going kind of fast here. How many states were there for these? Well, a spinning charge acts like a miniature, or acts like a what? A magnet, right? So anything that's spinning charge acts like a magnet. And then it's odd, Brandy, but these little spinning magnets, these protons, had how many energy states? 2. Okay. And without, here's a good question, PChem people. Without a blank, these energy states, right here, without a blank, these energy states are degenerate. Without a what? Let's give the PChem people a shot first before Andy answers your question. Without an applied, anybody? Andy. Randy. Without an applied, what is this big thing? Without a magnet. Without an applied magnetic field. Without a B naught in the math equations that are coming up. And there should be an arrow above it, but without an applied magnetic field, you're not going to see this splitting. And it needs to be pretty dang strong, too, in order to see this splitting. Otherwise, those states are going to be degenerate. Right? Because it doesn't matter whether there's nothing to be going against these little magnets. There's nothing to be working with or against the magnetic field if you don't apply a magnetic field. So that they would just be the same energy state. Okay, so those states, they're either spinning with the applied magnetic field, right? So the magnets are nice and lined up, so there's minimum energy, or they're repelling, opposite, like north lined up with north, higher energy. But no field, they're degenerate. Okay, so here is our big equation for that energy splitting. And we get spectra. So that means you've got 2 axes, and you get stuff here. You get peaks. Okay, this axis was intensity. How do you get this axis? What's changing? What is changing? What is that axis? That is a hard question. That's what we're going to talk about today. Okay, what is that x-axis? Okay, but we're getting there. Now Let's see if you can make the leap here. That, we're going to get spectra somehow, right? We're going to talk about that x-axis, but different protons had different chemical environments. Like if you have benzene, right? Each of those protons, but I guess, remember the boat and chair conformations? So that's kind of a trick question almost. They're not going to have identical. All right, they're not going to have identical chemical environments. Here, that would be a good one, right? All those protons have identical chemical environments. And what you're interested in is what are all the other little magnets around it doing? Okay, the charge distribution of like the electrons, for example. Okay, because any spinning charge is going to act like a miniature magnet, and only a magnet can interfere with another magnet. So that's why this whole shielding idea came in. So protons in different chemical environments right? If I have, what's the name of this? CH3, CH2, CH3. Propane, right? So I have got two methyl groups, one on each end. Do those have identical protons? Are the chemical environment, are those all the same? Yeah. Do you remember they're single bonds so they can spin? Okay, they're not double bonds, they're single bonds, so they're spinning. So you've got 6 identical protons, right? And then you've got 2 in the center that are also, those 2 are identical. But they are supposed to give rise to different peaks. It has something to do with this equation. What was changing? Which symbol? You're right, Alyssa. B naught, that magnetic field. They all feel a different magnetic field. All right? Even though they're all in the same sample tube, they're all in the same instrument, but CH2, right, he's being shielded by 6 other protons and all the electrons involved, right? So there's this interaction going on that we started talking about. Gave rise to these different peaks. We talked about how if that's what the energy splitting is, you apply a photon, frequency h nu, and we said that's in what region of the electromagnetic spectrum? In the radio waves, right? So, and that frequency of that photon is the same as the Larmor frequency, okay? That frequency of precession. So we get our, where is it? Here it is. We have our magnetic field turned on, right? And it looks like it's turned on the entire time. Okay. But then, so you turn it on. NMR tube's going there, right? Everything pops up in the same orientation as the applied magnetic field. Because there's only 2 energy states. So everything's in this. Is that me? What is that? See why you don't have cell phones? See, then you push a button and nothing even happens. That's what you get for Virgin Mobile, right? So how do I shut this thing off? It is off. Weird. Okay. So they're all like that in A, right? What do these arrows represent again? Whoa. What does one of these arrows represent? Ooh, my P camera, magnitude of what? Talking about one of these. This is, you guys don't, angular momentum. You guys, if you don't worry about that, that's too much information. You really don't need to know. But you had to use the, oh gosh, man. I wish I could figure out why this happens. think it has something to do with Java or something. Anyway, so what we were talking about is, here's where we start, right? With turning on, and this guy's always on. Okay, so it's permanent magnet sitting in that instrument. And then you get this precession of the angular momenta, right? And you kind of think of it as, if you're spinning like this, pretty much all Melissa's saying is, okay, just kind of wrap your hand around it, but look at your thumb. Your thumb is pointing the direction of the angular momentum. Okay? So the arrow would be going like this then. That would be the arrow. And that's what they're talking about. That arrow is this arrow. Right? They're the same thing. So they apply a second magnetic field, right? But it's not, it's a pulse though, right? So what degree pulse did we say? I don't know if we use this term. It makes it flop over 90 degrees, so it's they call it a 90-degree pulse, because the pulse shuts off once it goes over 90 degrees. And you can kind of see that from, right, it's bending down, B, C, and hit D. Okay, now it's, this precession is now going around the y-axis, 90 degrees. They should have kept the cone going this whole time, because it's precessing this whole time, right? And then they shut it off, and then it just kind of goes back to its ground state. But as it goes back to its ground state, it emits photons of what frequency? Radio waves of the Lamour frequency in the radio wave region, right? Okay. And the signal should start out, they're all in this excited state. It should start out really strong, and then the signal gets weaker over time. Okay. And we called that the what signal? All right, the signal starts out really strong, and then it just gets weaker. Well, we will apply the Fourier transform to this signal. The free induction decay. Okay, so a lot more physics there than we're getting into. But it's just a emission intensity, and it's getting weaker and weaker. And then, like Melissa said, you apply this mathematical operation to go from, hey, what frequencies are actually present that are giving rise to that decay? Fourier transform, and you get the signals, and you get the intensity of each frequency. Okay. So these frequencies, these Lamour frequencies, depending on the shielding, there will be different protons. That's what this whole table is all about. This chemical shift idea, these environmental effects, these environmental influences. Where did we drop off?
We stopped with, where's that example?
Okay, this is where I messed you up. Okay, this is where I changed a lot of stuff. So, okay, environmental effect type number 2. We talked about this one, right? The N+1 rule?
Yes.
Okay, so this is where I kind of mess things up for you guys. The name of the molecule to the right is tetramethylsilane. Right, and they're going to abbreviate it how? TMS, right? Tetramethylsilane, they abbreviate it TMS. So let's start with brandy. All the protons in this molecule are magnetically speaking anyway. Identical. They're all identical. You can almost, they're all identical. And therefore, Melissa will give rise to how many NMR peaks? 1. They're all identical. So there's nothing to do any splitting because they're all identical. There's only one group. Kind of look at it that way. There's only one group of protons. When we talked about, where did I draw propane? Drew propane somewhere. There it is. How many groups of protons are there in propane? You can classify all these protons. There's what, 3, 6, 8 of them. You can classify them into how many groups? 2. you've got your methyl group and your CH2 group. So, but TMS only has one group, and they're all identical. Where am I? Here I am. Okay. So an internal standards added all proton NMR samples. It's called TMS, tetramethylsilane. Why do you think this compound was chosen as the internal standard? To measure all proton chemical shifts from. So for some reason, we're going to do twice the work. Internal standard means you got to measure two signals, the signal from your sample and the signal from the internal standard. You have to do twice the work. Why? Hint, look at the equation for the Moore frequency. All right, well, we got to go back up and look for the equation for the Moore frequency.
But the magnetic fields would be the same for all protons.
Here. What was this? Here's the equation for the Moore frequency, right? What was this B naught again? The magnetic field that it felt, right? Okay, you have two NMRs. What if they, they both have TMS in them, they both have propane in them, whatever. So the chemical environments, all that stuff is the same, but the darn magnetic field that you're starting out with is different. They could be different strengths. They could be different, there's a lot. Why? There'd be a lot of money and a lot of expense to have everyone's NMR be exactly the exact same strength. That means the guys who are selling this stuff can only sell one resolution. Well, you're not going to make a whole lot of money doing that. This dude's going to come out with a much better one, and then he has to have a whole new axis. Oh, you use Joe's NMR, so we have to talk about different. Everything's all over the place. There's not one chart for everybody. So what we need is a way of taking different magnetic field strengths for NMRs, that instrument, into account. That's why they introduced the internal standard. And you measure two signals. Where'd it go? Different NMRs have different operating frequencies. They have different strengths. Spectra cannot be compared from different machines if they are reported in frequency units. Right? You can't compare them because they had different B naughts in the first place. Of course, if you have a stronger magnet, you're going to feel a different magnetic field strength than you would with a weaker magnet. Like we have a pretty weak one. Ours is called a permanent magnet. So you don't have to plug it in. It's a magnet. It's permanent. It's therefore convention with NMR spectroscopy to use units of blank, i.e. parts per million, for all NMR peaks. ppm, obviously, right? All chemical shifts are calculated the same way. Your peak position, minus TMS, or TMS minus your peak position, right? It's relative, divided by the spectrometer frequency in megahertz. So really, you're dividing hertz by megahertz. So there's your million, and that's where the parts per million comes in. Okay. So you end up getting your absorption intensity versus these chemical shifts. And it ends up looking like this. But the point is down here is ppm. So if you're going to do NMR and you don't have a bottle of TMS, you're pretty much screwed. Right? You need that tetramethylsilane. Okay. So that makes sense? So since it's not quite in your notes, you've got some writing to do, but that's the idea. Proton NMR wrap-up ideas. Under usual conditions, an OH proton doesn't split the NMR signal of adjacent protons. We've got this n+1 rule. You'd like to, there's a hydrogen sitting there. You'd like to call it as an individual group so it can do its, no, you can't. You really don't. And we'll have an example of that. We'll have an example of this coming up here when we do ethanol. But our FT NMR is a permanent magnet NMR. Researchers use much more powerful magnets, superconducting. Right? Here's the conventional picture of this superconducting magnet when they first came out. Right? How they could levitate other magnets. Okay, but now it seems common. It's no really big deal. It's not really that cool of a picture anymore because people have seen it so often. But anyway, these superconducting NMRs, like this guy, they've got this chain going across here. And what I wish is that I could also get a picture of the door that goes into this room, because they're going to have a big sign there that says, hey, you got a pacemaker, do not even come close. Right? So they can erase credit cards and all that kind of stuff. So our NMR upstairs, permanent magnet, cost around, I would say nowadays, around $75,000. These guys, several $100,000. But people are forking out money for them. Why? Why? Somebody know? Here it is. Let's make this huge. Then this is going to be huge. And if you have huge energy splittings, where's a plot of my NMR? Here's one. This is going to be huge. The idea is resolution. Man, just imagine the resolution you'd have. Just, and for those complex molecules, proteins and everything else, where you should see splittings, you really don't, right? You're going to see, well, we'll have an example of this coming up with doing our ethanol. Okay. A lot easier to see stuff, much cleaner. So that's the advantage. How about a disadvantage of these superconducting magnets? Can you think of one? The pacemaker idea, that's kind of bad, right? But you got to put up signs and stuff, but still, that doesn't sound so good. The price tag would be a disadvantage. But I think for me, the reason why, and we had this nice grant that I got hired here on, and I could have made an argument to get this, but I wasn't even going to mess with it. And the reason why is this white stuff right here. What is that? To get this thing to work, to get that magnet to levitate, to get that bottom magnet to superconduct, it needs to be really, really what? To this day, still, it needs to be really, really the other way, cold. And it was a great big deal. I would say like around 15 years ago that we finally got things to superconduct at liquid nitrogen temperatures. That's what opened this whole field up. And liquid nitrogen's still pretty cold. Then you got to be dumping it in the whole time. I don't want to do that, Andy. Right? I want to just plug the thing in and go away. So I made the argument, no, I don't want to mess with that. And it works fine. Okay. When obtaining an NMR spectrum, so there's what you recognize this, don't you? Yeah, NMR tube, right? Thin, narrow glass tube. When obtaining NMR spectrum, we have to make sure the sample's spinning. Why does it need to spin? Now there's some complex diagrams down here that give you the answer. But essentially, if you draw a magnet, right? North, south, and then you draw another magnet, north, south, and then didn't they draw these lines? Remember doing this kind of thing? You could put iron filings and stuff. You saw these lines, fields of strength, that kind of thing. Okay? And if you saw a lot of lines, the magnetic field strength should be stronger, right? And if you see less lines, it should be weaker. That's what's going on with these plots. And notice how they're trying to draw the difference between these lines to be equidistant. That's what they want. Now, the technical word for that is what? It starts with an H. Homogeneous. They want that they want that magnetic field to be homogeneous. Not an easy thing to do at all. So that's why you need to be doing this shimming and that kind of thing to try to get that field to be as homogeneous as possible. Pretty hard to do. So you gotta spin that thing because then, right, it kind of averages out. You gotta spin it pretty fast. So shimming's not near good enough. Let's take a look at ethanol. Okay. So there's the chemical structure of ethanol. I kind of answered my own question here. How many different groups would you say, Brandy, are in an ethanol molecule? How many different groups of protons with their chemical environments? 3. Everybody agree? Yeah, I'd say there's 3. I agree with that. Which group, of those 3 groups, Melissa, which group would you believe exhibits the most shielding? This is just something that takes used to. Which it's going to feel the most shielded. Let's back. You need a baseline to be getting this feeling. Okay. TMS. Here's TMS. You're supposed to think of this molecule as super shielded. He's really, really well shielded. And you've got a lot of, because what you want is a lot of electrons. The more the electron density, the more density of charge, the more shielding you got. They're magnets. You're gonna feel even less. So you can't get much better than this. In fact, you really can't. All you have are a whole bunch of methyl groups. You've got 4 methyl groups. It can't get any more dense than that. And all we're talking about is organic compounds, so carbons and hydrogens and oxygen and nitrogen, right? But we're doing proton NMR, so really you're worried about the positions of the protons and where they're oriented in the molecule and their chemical environment. Well, each proton is surrounded by other methyl groups, and they're all identical. You can't get any better shielded. This is as good as it gets. As good as it can get for shielding. I guess for proton shielding. Pretty much carbon too, I guess. I mean, that's pretty good. Okay, so now let me ask the question again. Which group is going to feel the weakest magnetic field? It's shielded the best. The OH is just out there on its own. So definitely not that one. CH3. It's the CH3. That's the feeling that you just got to get used to, and that's the thought. So the least would be the OH. So answers are supposed to be, the hydrogens, right? So these guys and this guy. Okay. 4. If solely chemical shifting occurred, so remember that's the one where the shielding idea. There's no splitting of peaks, it's just the shielding idea. Sketch a proton NMR spectrum of ethanol and identify the different groups. So we have 3 groups, so we better have how many peaks? 3, because they're saying that, hey, you don't have any of this splitting stuff going on, only chemical shift. No N+1 rule. Okay, so then draw the 3 peaks and include a TMS peak. Now their convention is to draw TMS where? Furthest to the right or furthest to the left? Furthest to, yeah, way over here. I think what they do, Oh, yeah. Yeah, there's 0. So a chemical shift of 0 is right here. Remember how they're calculated? You take, here it is, relative to TMS. So for some weird reason, right, they have 0 right here. Then all the shifts are going that way. So if you're really well shielded, you are right here. Does that make sense? Because that's where TMS is. So you can draw a 0. It's weird how, right, these arrows make it confusing. You've got a 0. So there, we're supposed to draw a TMS peak. And all those hydrogens are identical, right? So that should be a nice, pretty solid peak, depending how concentrated it is. I'm not drawing this very nice. They're a lot sharper than this, right? And then you drew a CH3, then a CH2, then an OH. And the intensity needs to be proportional. Really not the intensity, but the area under the curve is proportional to the number of protons. So CH3, I don't know, if I draw it like this, CH2 and the OH. So the OH has to be 1/3 the area of that CH3. How would you draw 1/3? Maybe. The CH2 needs to be 2/3 of it, or double the OH, something like that, right? That's, I'm trying to, and then this TMS peak could be really high or really low depending on just how concentrated it was. The instrument just needs to read it. It doesn't care about concentration. It just wants to know where it's at. Okay, so according to the n+1 rule, a peak is split into n+1 peaks, where n equals the number of identical protons adjacent to the group. Note that protons further than 2 carbons usually don't split. Taking both chemical shift and spin-spin splitting into account, now sketch a proton NMR spectrum of ethanol. Include a TMS peak. So we should have a TMS peak. We can draw, our methyl stuff will still be here. Our CH2 stuff will still be here. Our OH stuff will still be here. So let's start with CH3. Here it is. Here's our methyl. N equals the number of identical neighbors. So for the CH3, N is going to be 2, right? Because it's 2 plus 1 would be the number of peaks. So we better draw how many peaks for CH3? 3 of them, right? So I don't know. I mean, usually it seems to me like this middle guy is always bigger. I don't know. I just want to see 3 peaks. That's all I want to see. For CH2, how many peaks do you draw? Now, how many identical protons are surrounding CH2? Well, see, remember, he's too far away. He's too far away. So you have 3. So N is going to be 3 plus 1, 4. So you're going to have to draw 4 peaks for this guy. And now I kind of messed stuff up. Remember, the area under all this stuff has to be proportional to the number of protons. So I should have more area for the CH3 than I do for the CH2. So either I should draw this guy bigger or make this really small. I need 4 of them. I need less area, too. So 1, 2, 3. Let's make it bigger. We're going to talk about that, but just here. Usual conditions, OH proton doesn't split the NMR signal of adjacent protons. Nor is the signal of an OH proton split by adjacent protons. Just a general rule. So let's draw this bigger so I can make more sense out of the area, right? 1, 2, 3, 4. right? And OH is going to have 1 peak. And its area is going to be proportional to its number of them, right? So it's kind of hard to do. Oh, I forgot my TMS, but that's the idea. Okay, now notice how that proton on the H, right, he shouldn't have, they're saying that general rule, he doesn't influence, right, the CH2. But if you make things even stronger, you can get more interactions and get more peaks. And it looks like, oh, that's a bad thing because it's going to be so much more complicated. Yeah, but you want that information. And with a really high strength magnet, you can resolve it. So it's a good thing, even though it looks, you're going to have more information there. So we should have ppm down here, right? Signal over here. Okay. And then there's your homework. Pretty much the same question you had, but just change it to propanoic acid. And you've got that in there. Okay. All right, because that was a typo. I think it says the very last problem you guys have. Okay. So do the same thing we just did, but do it with propanoic acid. That's a homework question, or it could be on the quiz or something. Yeah, it's the exact same thing, but just do it with propanoic acid. Okay, so that's it.